the chain rule. This is it. It may look pretty straightforward, but this is probably going to introduce the most complexity this entire semester to our problems. The chain rule is incredibly useful, so useful in calculus that we will be using this the rest of the semester. Probably over 90% of our problems going forward will use the chain rule. So this is the chain rule, but let's take a step back and see where this comes from. So imagine you have two numbers, any two numbers. I'm just going to pick 2 and 5. Now, algebraically, what can we do with these two numbers? We have two numbers. In terms of algebra, what can we do with them? Well, something we can do is we can add them. You're familiar with that? We can subtract, multiply, and divide. Algebraically, meaning in terms of algebra, these are the 4 things that we can do with numbers, these operations. Now, in terms of the derivative, we deal with functions. Now, with functions, algebraically, what can we do with these two functions? Well, we can do the same thing that we do with numbers. We can add them. We can subtract, multiply, and divide. But in terms of the derivative, so concerning the derivative, when we're taking the derivative of something that's being added, well, the derivative distributes. That's how we handle taking the derivative of functions being added. If functions are being subtracted, well, the derivative distributes. That's how we handle subtraction. In the last lecture video, when you multiply two functions, that's the product rule. And when you're taking the derivative of two functions being divided, that's the quotient rule. So what else is left? What does the chain rule do? Well, the chain rule has to do with something that you probably had one section on in Math 151. And that's the composite. So you may recall, you probably had one homework on this in 151, the composite given by this open circle. So we would read this as F composite G. And what this specifically means is you're putting the entire function G into the function F. Now there's no composite for numbers because it doesn't make sense to say what is 2 composite 5. Because how can you put 5 into 2? So the composite doesn't make sense for numbers. It's something that applies to functions. And the composite, in terms of the derivative, is where we have the chain rule. So let's take a look at this function here. Hopefully what you're being able to identify at this point is that you have a power function plus a log function. And remember, these things are important so you know which derivative pattern to use. But what about this function? What do you see here? Well, again, we have our logarithm function. You can see the ln for natural log. And we have our power function. But this time they're not being added. They're not being subtracted. They're not being multiplied, nor are they being divided. This is a composite. We are putting the function x squared into the function natural log. And what's common to say with this? It's common to say that the outside function is the log, and the inside function is the power. Because the power function goes into the log function. And this is where the chain rule applies. So let's check it out, how we would use the chain rule on this. And something that's important to recognize going forward as well, not just for this section, is the derivative operator. Now this operator is telling you take the derivative of what you see next here, but there's something else that this operator is telling us. It's telling us we have to take the derivative with respect to x. And for all the problems that we've done so far, our functions have also had an x in them. And so there's a match here. We have these x's. And the derivative of log x is one of our x. That's one of our derivative patterns. So what we're going to do is we're going to take our function log of x squared, and we're simply going to define a new letter. I'm just going to call it u, and we're going to say u equals this x squared. And when we do that, we can then write h in terms of u. So again, we have log of x squared. We're going to take x squared and define it to be a new letter. By doing that, the log function is now in the form of our pattern, our derivative pattern. Because our ultimate goal is to use the derivative patterns. So we need to get this somehow to be used by this. However, there's a problem here. Because now that our function is a function of u, we now have, when we apply the derivative operator, we now have a letter mismatch. Because the derivative operator is saying take the derivative with respect to x, but our function is of u. It's not of x anymore. And so there's a problem here. And just to give you an example of this that may be something more familiar, let's say I ask you, what is h of t when t equals 4? Now, you may be thinking, well, I'll just plug 4 into this. But this isn't h of t. It's h of x. When I'm asking for h of t, there's a letter mismatch. And so you should rightly question then, do you mean x equals 4? Because the function you're giving me is of x. There's a mismatch in letters here. And that's what's happening here with our derivative. The derivative is saying take derivative with respect to x, but our function no longer has an x in it. And this is where the chain rule kicks in. Because the chain rule is what deals with these mismatch in letters. So notice the chain rule right here. Remember, our function name is h. dh over dx means the derivative. And the first thing it has here is dh du. In other words, take the derivative of our function, but with respect to u. And then it says, take the derivative of u with respect to x. So the chain rule is dealing with this mismatch in letters. So we have u equals the inner function, which then gives our outer function of just being log u. And we're going to use the chain rule. So the derivative, so this first part right here of the chain rule, dh du, this is the derivative of u, the derivative of h with respect to u. And so I'm going to do that down here. So now we're taking the derivative with respect to u. So notice the derivative operator now has a u in it, because that's what the chain rule has. And there's no longer a mismatch in letters. And now we can use the derivative pattern. And we know the derivative of log is 1 over u. And that is dh du. That's what we put right here. Now for du dx, well, that's what u equals x squared is for then. Because we'll take the derivative of u with respect to x. And again, notice there's no mismatch in letters anymore. And the derivative of x squared is 2x. So we have dh du, which is this piece here. We have du dx, which is this piece here. And now we just multiply these two together to get our derivative. Now, there's one more thing to do here, because our final answer we want only in terms of x. So the last thing to do is to take u and plug it back in to get our final answer. So all I did was plug in u, and now we'll simplify, and that's our derivative. Let's check out another one. E to the x cubed. Now, the first thing you want to ask, is there a function inside a function? Because that's what a composite is. You need to be able to recognize when a composite is happening so you know to use the chain rule. When you have a function inside another function, you have to use the chain rule. So we have a power function, x cubed, and its power function is being put into an exponential function. Now, what we want to do is use the derivative patterns. And to do that, we're just going to take the exponent and just call it u. Because when we do that, our function is now in the derivative pattern. This is our derivative pattern for exponentials. You know the derivative of e to the u is itself. However, doing this change of letters means we have to use the chain rule. So the derivative of u with respect to x is 3x squared. That's our power pattern derivative. And the derivative of u is our exponential derivative. It's e to the u. And we're going to take these pieces and put them into the chain rule. So we have du dx, which goes right here. And we have dh du, which goes right here. And so we'll plug those in. And now that we've plugged them in, we'll then replace u with our definition to get our final answer. Let's check out another one. What do you see here? Do you see a function inside another function? Can you identify the functions at play here? These are all things you have to be able to do. There is a function inside a function. We have a log function inside a power function. And so what we're going to do is we're going to define the inner function as u, which then means h is just u squared. And notice what's happening here. Our original function is not any of our derivative patterns. It's none of them. There's nothing we can do with this as it stands like that. However, if we break it into these two pieces, notice that both of these pieces are our derivative patterns. We can do something with this. So we'll take u. We'll take the derivative with respect to x. The derivative of log is 1 over x. That's the log pattern. We'll now use the power pattern on u. dh du is 2u. The derivative of u squared is 2u. We'll now take the chain rule and plug in these pieces. So dh du is 2u. du dx is 1 over x. And then to get our final answer, we replace u with our definition then. And of course, we'll simplify and clean it up. There's nothing more to do here. That is our final answer. Let's check out this one. What do you see here? We have a log function. we have a power function inside a power function. And they're all being multiplied together. And what do we do with multiplication? We use the product rule. This is a product rule with a chain rule. So using the product rule, we break this into two factors, f times g, where we'll identify f as the log function, and we identify g here as the composite function. And once we have f and g, we take the derivatives. So f is one of our derivative patterns, and so we can get that derivative. The derivative of log is one over x. However, g is not one of our derivative patterns, and we got to do something about that. And that's the chain rule. So we're going to take the inner function and define that as u. When we do that, g becomes then just u to the 10th. And notice, g, we can't do this derivative. But these, we can. That's why we go through this process. This is how you get this derivative. So the derivative of u, we have a power function and a constant here. So the derivative of u is 2x. Remember, the derivative of a constant is always 0. And the derivative of u to the 10, another power function derivative, is 10u to the 9th. And now that we have these pieces, we plug them into the chain rule. So dg du, the derivative of g with respect to u, 10u to the 9th. And du dx is 2x. And then finally, we substitute back in what u is. Remember, we called u x squared minus 4. And so we plug that back in for u. And here is our derivative. Now I'm going to clean this up a little bit because 10 times 2 is 20. And so for g prime, we have our chain rule derivative. And now that we have these 4 pieces, we can now do the product rule. And so we'll just plug our stuff in. F G prime, which is what we just did the chain rule on. F prime. And then G. After we've plugged everything in, we'll try to clean it up. There is a greatest common factor here of x squared minus 4, all raised to the 9th. That's our greatest common factor. And here is our simplified answer. That is the derivative. So, something you may be noticing is problems are getting longer. Answers are getting more complicated. This is the final answer. There's no making this look any simpler. So question 1, what is this derivative? So, notice that this is not the exponential pattern, because the exponential pattern is just due to the x. There's nothing we can do with that. We don't have this derivative. However, we do know the derivative of 2 to the u. So that means we're going to take the inner function. The inner function here is the log function, and we're going to call that u. When we call the inner function u, the outer function, the exponential function, is now a derivative pattern. And so is u. These are both our derivative patterns now. And so we'll take their derivatives. The derivative of log x is 1 over x. The derivative of 2 to the u is log 2 to the u. We'll take these pieces and put them into the chain rule. And once we put our pieces in, we'll then replace u with what we defined it to be, so that everything is back in terms of x. And there's our answer. So in summary, there is only one thing to say: chain rule. And this is probably going to be the simplest summary for the entire semester. However, don't be deceived by this simplicity. The chain rule is enormously powerful, and we will use it the rest of the semester. So make sure you're doing your best to burn this into your brain. And as always, if you want to see more of these problems worked by hand, make sure to check out the practice video. That's the end of this lecture.